Okay, today we're going to be looking at Chapter 8, which deals with delocalized electrons. Now, all we mean by that, in a basic form, is that the electrons are going to be free to move about throughout the entire molecule. Now, it will be electron pairs. Now, what I mean by electron pairs is pairs like on a nitrogen, or even the pairs that make up a pi bond. When we can have a situation where they move around, we have delocalized electrons. Great example of that is here on this little the CO on the end. Now, back in General Chem, when we were doing Lewis structures, we would have actually said that we had two different ones, where the negative was distributed between those two little electrons. So basically, delocalized electrons are the resonance structures that we had from general chemistry. Okay, now where this came into play and the reason it's so darn important is it really actually started to pop up when early chemists were trying to figure out what benzene actually looked like. So they knew early on that benzene had a formula of C6H6, which gives it 4 elements of unsaturation. So that could be something like 4 double bonds or 3 double bonds in a ring. So these were both possible examples. Matter of fact, at the time, there was like 7 different ways they put this together to try to figure out how it was made. These are about the only 2 that still kind of make sense of those 7. All right, but we had a small problem. When we actually do a substitution reaction on benzene, we only get one product that has just a single halogen on there. So C6H5Br, there's only one way of making that. But when we replace 2, we have 3 distinct different possibilities. Well, both of these kind of fall apart when we do that. What I mean by that, if I were to take the one with the 2 triple bonds, replacing 2 hydrogens with bromines, I could put both of them on one side or one on either side. So there's only 2 possibilities. Possible. So there's no way that is benzene. Now, if it's a ring like this, and you notice how they're drawn specifically a double bond, single bond, double bond, if I replace 2, I can have them catty corner, totally across from each other, or right next to each other. But if they're right next to each other, there was 2 ways to draw it, with a double bond between them or a single bond between them. So that would give 4 products. So this also isn't a possibility. However, there was this guy, Kekule, who came out and said, well, actually, those last 2 are the same thing. It's just that that double bond is moving around so fast that it is sometimes a double bond between the bromines and sometimes is a single bond between the bromines. And we kind of agree with this now. Matter of fact, when we actually see benzene drawn more often, it will be drawn as a perfect hexagon and oftentimes with a circle in there. And that circle comes about because those p orbitals that make up all those double bonds, well, they don't make 3 pi bonds. They don't just make pi bonds between every pair, and that doesn't move around. What actually happens is the pi bond that forms between all 6 simultaneously, and it actually makes a ring. So that is actually a single pi bond that occupies the area above and below all 6 carbons. Now, we see this in other places. There's benzene drawn out more precisely. But though we see this in more places, so we're going to look at that some more. But we're just going to do some terminology right now. So when we actually draw our benzene with that ring or the dashed lines or the circle, we are drawing what we call a resonance hybrid or a resonance structure. And that is actually what we think this molecule looks like, because we don't ever see signs that there's a double bond or single bond moving around. It's almost like the carbons are bound by a 1.5 bond. But that's where these resonance contributors come from. We're saying, well, it's a double bond part of the time and a single bond part of the time. But the weird thing is, this word resonance contributor, the molecule never actually exists like this. It doesn't exist at all. It's never a double bond and a single bond. It's always somehow both of these. So the resonance contributors aren't real structures. They just represent how the electrons might be arranged at a given moment in time. It's just that the electrons are constantly moving. It never stays there. Now, even though I said it doesn't represent a real structure, we will see that oftentimes in our mechanisms, we mostly draw the resonance contributors. We hardly ever draw the hybrid structures with the dashed lines. All right, so drawing our resonance contributors, we're always going to draw it in one particular location. What I mean by that, we're always going to draw full bonds, full electron pairs, never going to have any dashed lines. The dashed lines are a sign of our resonance hybrids or the resonance structures. We hardly will ever draw these. And when we're actually drawing mechanisms, we will definitely be drawing the contributors. Not necessarily both, but the one that's more important to our mechanism. All right. Excuse me. Now, our question is now, does a pi bond help a carbocation? What I mean by that, let's go back to what we first learned about carbocations. And if I were to make up one and actually attach it to a carbon here, I would say that was a very unstable carbocation because it's only a primary carbocation. However, what happens if I, off of this other carbon, what if I put a double bond there? I'm going to go ahead and put hydrogens out here. All right, does that help it, hurt it? What do you think? Well, here's something neat that can happen. I think that changed my ink color. Could let that double bond move over here. And it might be inclined to do that because that does represent electrons, a negative charge, that's going to move towards the positive. But if that happens, this structure kind of changes. And all I'm going to do is draw where that double bond moved to. It's now over here. And now technically, the positive is on this side. All right, notice what happened though? That resonance contributor actually has now moved the carbocation from just being on one carbon to being on a second one. That definitely will actually make the carbocation more stable. So even though this is still a primary, and this is still a primary carbocation, it's actually primary allylic because these two actually go back and forth. So we do see that the carbocations do actually stabilize it, or the double bonds do stabilize our carbocations. That resonance contributors or resonance structures will actually balance it out. So neither one of these carbons are ever truly positive. Both of them are simultaneously slightly positive. Now, if I put too much space between the double bond or another carbon, I don't get that stabilization because moving this thing over here doesn't affect that cation. We would have to have the cation on this location. So it has to be allylic, it has to be right next to that double bond, or else it doesn't give us any benefit whatsoever. All right, how about if there's more than one double bond? Well, that's what we're seeing here. We could actually move that over, which swaps the double bond, moves the positive in there. We could do that again. So there are 3 different resonance contributors for this structure, and there's 3 different carbons that carry that carbocation charge. Very stable by comparison. Okay. The neat thing about our resonance contributors, we're going to find that the more we can draw, the more stable we have, but also we're going to see that they affect the physical structure of a molecule. Like what I have here is an amide, that's AMIDE, carbonyl attached to a nitrogen. And looking at that nitrogen, it would be easy for you to think that that must have a trigonal planar shape because it's got 3 things attached to the nitrogen and a lone pair. And if we were to say that, we would say that being that it's trigonal planar has a nice little 109 degree bond angles. However, this one does not. It actually behaves more like a double bond sometimes, and this actually behaves like it's got trigonal planar structure. Now, the reason that is that lone pair, even though it's normally would be expected to find a pair of electrons in a hybrid orbital, this pair exists in a p orbital because it is able to go into a nice little system with this oxygen. So even though this resonance contributor has a positive and a negative, and this thing is a very stable molecule, that would tell you that we actually have an equilibrium that looks more like this. But it does happen enough because the oxygen is very electronegative, and that does affect the nitrogen some. It actually will affect the reactions of that nitrogen. But again, if I put a CH2 or a carbon that's sp3 hybridized between the two, I don't get that benefit whatsoever. Now we have a lone pair that actually acts independent, and then our oxygen double bond is independent. All right. Turns out triple bonds do the same thing. Triple bonds, which are made up of 2 pi bonds, we could have 1 pi bond actually react in that system. So if I were to have an anion drop its electrons in here, then I could move this one of these 2 up there and spread out that charge. So the only thing I really need to have is a pi bond available, or electrons in a p orbital. Okay, something that affects our stability is whether or not our resonance contributors are stable molecules. All right, now this particular example is a great example that shows us why a carboxylic acid may not need a resonance contributor to explain its stability. Matter of fact, this particular resonance structure is very unstable because it has those separated charges. It's very much going to prefer to go backwards. Very little bit of this is going to go forward. However, as we know from any general chemistry class, acids are things that give up H's. And if this carboxylic acid gives up an H, it becomes a carboxylate ion. And that would have a negative left behind. And that negative is not going to be very stable if it was all by itself. But this particular one can resonate back and forth. We can drop a pair of, make a double bond here, move this up, and now we've moved the negative to a different position. That carboxylate ion is very stable because it has those equal resonance contributors. All right, we see that even on complex systems like this. I have 2 double bonds in there. They will form systems, but we got 2 things that could happen here. I could actually start by having this lone pair attack here, or I could have this pair come up there. Now, the one that starts the attack ends up giving a positive. So if I actually were to start at the carbon-carbon double bond, I would end up having a carbocation, and then this charge would cause that lone pair to move up to the oxygen, so the oxygen would be negative. And if I went the opposite way, the oxygen would end up as a cation, and we get a carboanion. All right, we could predict stability-wise that this one would happen a little bit easier based on the fact the oxygen is electronegative. So being that oxygen is more electronegative than carbon, it's going to accept being a negative a lot easier than a carbon would. Matter of fact, we don't even really see that happen. But even though this is an unstable ion, it would actually indeed happen, at least to some degree, a little bit. Okay. We also see that with just any old lone pair. So oxygens can actually give up its electrons easily and move around. And even though oxygen is electronegative and would prefer to be a negative charge, this would actually happen to some small degree. So we're going to see that we can move these electrons around a little bit easier to make structures that, while they're not stable, they will help explain what's going on in chemical reactions. Same thing happening here. All right, so this delocalized energy being related to the delocalized electrons is going to help explain some stability. So when I can actually have more than one equivalent or stable resonance contributors, I will actually delocalize the energy between the 2. So what I'm talking about is here with this carboxylate ion. I don't really have a situation where the oxygen's totally on one side. It's always going to be between the 2. And since these are both the exact same stability, we expect both of them to get that distribution of that negative charge. Now, if I have a situation where one of my molecules is very stable by comparison, I pretty much don't really see this too often. So we'd have a nice little situation where the reaction definitely favors going backwards. We will actually see this occurs just to actually explain some mechanisms, but we don't expect it to be staying that way very long. And same thing happens with something like butadiene. Butadiene is very stable, having a, 1,3-butadiene, double bond, single bond, double bond. But we will see that we can explain some reactions by allowing the electrons to either go to the left or to the right and making either one side negative and the other side positive, or the exact opposite. But since both of these two ends are very unstable by comparison, we really don't expect it to happen too often. Most of the time, you're going to find butadiene just like that, and that's how it's going to be drawn. But carbonate, CO3 2-, those negative charges do move around between those three species, and we see that explains the stability of a carbonate ion. Okay, how about this? Can we predict one of these being more stable than the other? All right. Right off the bat, I see a primary carbocation on both these, which looks the same, but both these are allylic, so we know that double bond will stabilize it. So let's look at what resonance contributors these will form. So all I'm going to do is just have this thing move, so I could say a second reaction here, or a second species. We're just going to move that double bond from there to here and move the positive over. Now, this particular one, being secondary, is a little bit more stable, but we are just going to exist simultaneously. So I'm doing a two-way arrow, not saying one side's more favorable, because both balance out that positive charge. Going to do something similar over here with this one. Same type of thing. Turn that into a single bond, turn this into a double bond, and then put a positive there. And another nice little equilibrium. All right, so they're both allylic cations, but we got an allylic that's primary or secondary. And here we have an allylic that's primary or tertiary. And just because of that, this one's going to be a slightly more stable. Now, do remember, being a resonance contributor, neither one of these cations truly exist. What actually exists is a nice little resonance contributor. I'm not going to draw the positives. I'm not even really going to draw both double bonds, because that's a CH2. What I'm going to draw is the dashed lines that make up where those double bonds are. And then instead of a positive, I use the little Debye symbol, so partial positive. All right. Now, where this factors in, and reason it's so darn important, is because it's going to actually make a major change to how our compounds react. What I mean by that major change, if I were to look at cyclohexene and figure out how much energy it takes to go from cyclohexene to cyclohexane, I find that that pi bond actually only occupies about 28.6 kilojoules of energy. All right. As interesting as that is, the more important thing is we see that cyclohexatriene is not 3 times as high. So that's where this number came about. They just tripled this. That's just times 3 equals this. And that would be the predicted amount of energy in those pi bonds. Well, this cyclohexatriene is not the same as benzene on energy, because benzene only releases about 49, a little bit more than, not even quite double this, really. All right, so that big difference must be explained in how those electrons are being delocalized. Benzene's not acting like a bunch of, or not acting like 3 pi bonds. It's acting like something else. It's a system. All right, let's see if we can make sense out of this. Now, I did explain earlier that it's mostly a ring, and we're going to say that still is the case, that the p orbitals of benzene form a system that makes up that pi bond. And we're going to say that's exactly what happens here. All right, but let's do some terms, see if we can make sense out of why that is. All right, so doing a little bit of review here, we have right there what happens with pi bonds and how they're made with regard to uh, just ethylene. So two p orbitals overlapping to form that pi bond. Well, let's take this up a step further and talk about some of the terms that are going on here. So we do know that when we do this, we get a node for each level as we go up. And that node's where we make an antibonding orbital. So if we remember from general chemistry, we always have pi bonds and then antibonding pi orbitals. And that's what's represented with that node up there. Now, it's not just that a single node creates an antibonding orbital. What actually happens is whenever we have this, we always have a situation where, see, my mouse is actually failing to work on me for some reason. But we have a node, one node for each level we go up. But when we split our two orbitals in there, the lowest orbitals are always bonding orbitals, and the upper ones are always antibonding orbitals. Well, let's expand this to something more complex. This is with just CH2, so alkene. Let's look at that butadiene. So butadiene was carbon double bond, carbon single bond, double bond. Now, each one of these carbons has a p orbital, so that would create a row of 4 p orbitals. So 1, 2, 3, 4. When we create a pi system for butadiene, then we're going to actually take all 4 of those p orbitals and allow them to overlap. And those 4 p orbitals would create a system with 4 of 4 pi orbitals, which is what this is representing here. It's representing the 4 pi orbitals that are created in butadiene. All right, but what we're seeing is there's a single node and the energy level higher than that. There's 2 nodes above that, and there's 3 nodes as you go up. So these little dashed lines are representing the nodes inside the pi orbital, and they just get 1 more as you go up. And since there are 4 pi orbitals, 2 of them will always be bonding orbitals and 2 of them would always be antibonding orbitals. And we get a nice little distinction or distribution. Well, since we're talking about that aromatic thing, we're going to see that benzene even does this. Now, what I mean by benzene does it, let's think about what the shape of benzene looks like. It's that hexagon. It's a ring. Well, that does mean that when we look at benzene, it's got p orbitals that are going to be arranged in a hexagon. And when I showed you earlier and I showed that it lined up and made the ring, that's really because we would have one of these things that shows all those fully in sync with each other and forming a nice little ring. That would be, I should have that down here at the bottom because that would be very stable, very low in energy. If I did them like on the previous slides, they did it with color, and heck, I can do that. What I'm going to do is just color in one side of these. All right, but just like the other ones, as we go up, there's going to be more than one node added. The weird thing is, on benzene, though, because it's a ring, and I'm going to draw this as a hexagon, and then we'll add the p orbitals on here in just a second. Let me draw a better hexagon. Because when I actually put a node in benzene, there's actually 2 ways I can do it at least from the quantum theory point of view, I could actually, and I'll do it red just so it matches up those other colors, I can have that node go right between the bonds. So the 3 carbons on the top, those p orbitals are in phase, and the 3 bottom ones are on a different phase. Or I could have the node go right through 2 of the carbons. And both actually work. I'm not going to bother to do those figure eights. They'll mess it up. So both those work. So there's actually 2 different ways we can actually put that single node in there. And the same thing happens if I go up another level with 2 nodes. Because the nodes have to be oriented off each other. What I mean by that, they kind of have to be 90 degrees to one another. So I could have that one like we did right below. And since the other one has to be 90 degrees, it's going to go right through. And technically, this one, if I were to mirror it up here, I'd get the same thing just ever so slightly rotated. So what we're going to see happens instead is we're going to have a split that goes through 2 different bonds. So never goes through a carbon atom on this one. Both of those split between bonds. And then up here, this highest one actually just has 3 nodes. So node, node, node. All right. Neat thing is, we won't need to necessarily worry about drawing these out per se. We just wanted to actually realize that those 6 carbon atoms with those 6 p orbitals create a pi system. And that pi system is what gives benzene what we call aromatic properties. Now, what we can do that's actually a little bit more beneficial is make molecular orbital diagrams that kind of represent these things. Because that's kind of what these are. These are 6 different pi orbitals. And since benzene had 3 pi bonds, we have 6 electrons that go in there. So only this orbital and these 2 actually are actually filled at any given moment. But we're actually going to see that this will pay off on some of this explanation later on to why certain molecules are more stable than others. Because benzene, while yes, it is aromatic does mean stable. Why is benzene stable? What makes it so special? And yet something else that's a ring, I'm going to go with 8, and I'll still alternate it. Make that a little bit better drawn. Turns out, even though we got double, single, double all the way around in a ring, this one is aromatic. And this 8-membered is not. All right. Turns out there's a few rules that we find always apply, and I don't have to do any drawings or anything. I just got to answer this stuff, these questions. First thing, I need to make sure I actually do have a ring. And every member of that ring must have a p orbital in its hybrid structure. So if it's ever has any sp3s, it cannot be aromatic. So it has to have an available p orbital, and the molecule must be planar. So it has to be flat. And then if you've answered all 3 of these, and technically both these fit that category, this would be cyclic, that's cyclic. P orbitals, because there's pi bonds, there's p orbitals on every single one of these. So both locations are cyclic and p orbitals, and it could be planar. Well, that one definitely is planar, and we could have that 8-membered ring on a plane. So planar is a possibility. So once you know all these 3, the next thing you want to ask is there an odd number of pairs of electrons? And we have 1, 2, 3 pairs of electrons, 1, 2, 3, 4 pairs of electrons. The odd number is darn important. And just because of that, this one is aromatic. Now, these diagrams help us explain why it needs to be an odd number of pairs. Turns out when we arrange these, you're always going to have a single way of drawing it that has everything in phase. So there's only ever one pair down here. But as you go up on rings, there's always two ways to put a single node. There's always two ways to put a second node. So these are always duplicated. So you're always going to end up with an odd number if you fill up an entire set of orbitals, because you got one pair and then two pairs. That would be an odd number. Another two pairs would still be an odd number. So as long as you have an odd number of pairs, you're going to be aromatic. All right, so we already answered that cyclooctatetraene was not aromatic. How about cyclobutadiene? Well, we got our four things we got to ask. Does it have p, or is it a ring? Yes, it is a ring. Does it have p orbitals all the way around? Yes, it does. And is it flat? Yes. So it meets all those previous categories, but this one only has two pairs of electrons on it. And because it only has two pairs, it is not aromatic. Now, this one is more properly called anti-aromatic. And all that means is when we say anti-aromatic, it fills those first three things, but not the last one. And anti-aromatic compounds are very, very unstable. They'd rather rip apart and not do anything. So cyclobutadiene typically reacts very quickly, breaks this bond or the other single bond, and then opens up the ring. All right, weird thing is, even though this fits all those same categories, it's not anti-aromatic. You see how it's drawn bent now? It's not drawn like a stop sign. The reason it's drawn that way is because the 8-membered ring is big enough that it doesn't actually have to be planar. So it is a ring, and it does have p orbitals. And if it was planar, it would have an odd number, and it would be anti-aromatic. Anti-aromatic is ridiculously unstable, so what happens in this case, it just becomes non-planar. And I'll just put an X there. And by being non-planar, now it is non-aromatic. You really have to be a small ring to be anti-aromatic, where you can't actually be anything but planar. But if you are bigger than 6 carbons, it can be non-aromatic because it just doesn't go to a planar form. All right, so that's anti-aromatic. How about these guys? Notice what I got here. I got some cations and anions. All right, so let's see if we can decide what these are. All right, well, the first one is probably the easier one to see once you realize that that's a hydrogen and that's a hydrogen. Because if those are both hydrogens, that location doesn't have p orbitals. No p orbitals. And therefore, non-aromatic. All right, but that positive is represented by a p orbital. We've always said that in the past, and we still do here. All right, so this could be flat. It could be a ring, or it is a ring. It could be flat. It does have p orbitals all the way around. So is it aromatic? Well, it has one pair of electrons and one pair of electrons, and that's not a pair of electrons, so this is anti-aromatic. All right, but what about this? In the past, we always said when we had a lone pair of electrons, they exist in an sp hybrid orbital. In this case, since we would predict this to be probably a hydrogen off here as well, we'd expect that to be an sp3 position, because that's kind of what we've said. Anytime we have a lone atom and it's got 3 things on it and a lone pair of electrons, that lone pair occupies a hybrid space. So we would actually say sp3. When we have a ring, though, that's not necessarily the case, because on this ring, if I were to take that lone pair and count it as part of my ring, I have a 1, 2, 3 carbons. It is aromatic. Matter of fact, it's so aromatic you will sometimes see that cyclopentadiene anion drawn like that. Because what that's representing is that negative actually moves around. It is going to resonate in all these different locations. What kind of happens? I think I have this on the next slide. Yeah. So what kind of happens is that moves down here, moves the double bond, which causes that double bond to move up, make the negative. But the negative eventually moves to all 5 locations. So all locations kind of have that negative charge, very stabilized, and the ring is aromatic because we have 1, 2, 3 pairs of electrons in it. Now, we can't say all rings are always going to be aromatic or not, but we can say if it's flat, has those p orbitals, we can just flat out count the pairs. So these polycyclic rings, if we count the electron pairs, 1, 2, 3, 4, 5, aromatic. 1, 2, 3, 4, 5, 6, 7, aromatic. 1, 2, 3, 4, 5, 6, 7, 8, 9, aromatic. All of these polycyclic rings on this page are aromatic simply because they have an odd number of electron pairs. Our anions and cations aren't always one way or the other. You do need to count it out. So cyclopropene, ridiculously unstable, H and H would definitely be non-aromatic. Same with cycloheptatriene. You got a CH2 right there, so non-aromatic. All right, so let's rip off one of the H's and either take the electrons with it or leave the electrons behind and see if that makes a difference. All right, so if I'm looking at the anion, the last time we saw an anion, the cyclopentadiene anion was aromatic. So you might think this anion is too, but if you think about it now, 1, 2 pairs of electrons. That is anti-aromatic. Yet the cation one has just a single pair of electrons. That is aromatic. And same thing happened here on cycloheptatrienyl cation. There's 1, 2, 3 pairs of electrons, so aromatic. On this one, 1, 2, 3, 4, anti. Now, the interesting thing on these two anti-aromatics, since anti-aromatic is very bad, we want to avoid it if possible. And here's the weird thing. Remember back when we first learned about lone pairs of electrons, we put them in hybrid orbitals? Well, if this is out here in a hybrid orbital, it can't be part of that ring. So it's not anti-aromatic. It's actually non-aromatic. And same thing happens here. We would just put this out of the ring, and now it becomes non-aromatic. All right, here's where this really pays off and actually helps us understand something. So if I look at a typical cyclopentane and actually analyze its pKa, I find its pKa is pretty much the same as we find for any alkane. Alkanes don't really have their H's come off. They don't form stable anions, so ridiculously high pKa's. But if I look at cyclopentadiene, only thing different is it has those 2 double bonds in it. It actually has a pKa of 15. It's actually a weak acid. And the reason it is because if I rip off this H now and leave that negative charge behind, if you think about it, this negative charge could now go into the ring and make a aromatic system that is so stable that is able to rip off quite easily, and it drastically affects our pHs. We even see that on some of our heterocyclic compounds, or heterocyclic just means rings with other atoms in there. Now, when we introduced nitrogen in the past, we always talked about them being basic, and it is because that lone pair can actually attack something like an acid and neutralize it. Well, we're going to find that pyridine and pyrrole don't actually behave exactly the same as those. All right, the reason it is because of where the lone pair is. On pyridine, that lone pair is out in a hybrid orbital. And I can kind of predict that because if I look here and see that there's a double bond going to the nitrogen, I know this nitrogen must have a p orbital that's making up that double bond. So that lone pair can't be in a p orbital. That lone pair must be in a hybrid orbital, and it's sticking off to the side. Now, we will see that this ring structure creates a little bit of hindrance. So this is not nearly as basic as a typical amine is. It's still basic, but that ring actually somewhat protects it. The double bonds in there almost hide it. They create so much of an electron cloud that nitrogen's a little bit harder to react as a base. All right, let's back up here though. Where are those lone pairs on pyrrole? Well, if we think about this, that would make 1, 2, 3 pairs of electrons if it's part of the ring. And on pyrrole, that's exactly what's happening. That lone pair is inside the p orbital and it's inside part of the ring. And because of that, that lone pair is not available to behave like a base. So we see that pyrrole is not going to really behave like a base. Now, furan and thiophrene do essentially the same thing. One of those pairs stay inside the ring. So even though an oxygen and a sulfur have 2 pairs of electrons, really only one pair is really available to act like a nucleophile or do any other reactions. The other pair is stuck hanging out in the ring, making up part of the aromatic system. Now, if I go bigger on pyrrole or furan and thiophrene, so if I go to a 7-membered ring, let's see, 1, 2, 3, 4, 5, 6, 7, 8. I can't count, can I? Let me get rid of that. 7-membered ring. 1, 2, 3. And then I need 4 up here. Bam, bam, bam. That'll work. 1, 2, 3, 4, 5, 6, 7. That's better. And now I'll put a lone pair here, and I'll go around. All right. But if you think about it now, we would have 4 inside the ring. So it's actually not right to put those pair inside the ring. That particular heterocycle, those lone pairs are actually out here and they're somewhat basic because if they were to go into the ring, they'd make an anti-aromatic ring. So we're going to leave them out, make a non-aromatic, and now all of a sudden that nitrogen behaves more like a typical nitrogen and therefore somewhat basic. All right, so we see that pops up in a lot of cases. And right now in this chapter, we're mostly going to focus on some ideas, whether or not if it's acidic or basic, or if it's aromatic. We just want to know, is the lone pair going to help make it aromatic or is it not? So like on quinoline, we have 1, 2, 3, 4, 5 pairs of electrons if we count just the double bonds. That's an odd number, so that nitrogen's lone pair stays outside. On indole, 1, 2, 3, 4, even number of electrons. That makes it 5, so that stays inside the ring. So indole, the lone pair is in the ring, less available to be a base. And we can do that on any one of these. You just actually look at it and you want an odd number of electrons to make it aromatic. And anything else we leave outside the ring in a hybrid orbital. All right, let's go back to our double bonds, and we're going to talk about some terms real quick. So dienes are just alkenes, or is an alkene where there's more than one double bond. 2, that's where the di comes from. And they could be isolated. Isolated simply means that you got a double bond, and then later on in the molecule somewhere else, you have another double bond. Conjugated dienes are a little bit more interesting because they're only going to be separated by a single bond. We're going to see that these behave a little bit different on chemical reactions. Isolated dienes pretty much just react like we would expect them to. So an isolated diene, if we react that with hydrogen and actually get that heat of hydrogenation, we'll find this is almost exactly double what a standard alkene is. So these actually do and behave as 2 separate alkenes. The conjugated system actually behaves differently. Got a lot lower heat of hydrogenation, so there's something different going on because they are, for some reason, more stable. We also see something else that's kind of odd. What I mean by odd, even though this structure shows a single bond between the two, we will find it doesn't necessarily always behave like a single bond. It's too short for one. That single bond between the two double bonds is shorter, but we're going to be able to see that we can explain a lot of these properties just by looking at a few things. So here's what I mean by the shorter. When I have a single bond, a carbon-carbon single bond, it's always going to have a bond length about 1.5 angstroms. If I put it near a double bond, it's still right about 1.5 angstroms. It just goes down a little bit. But as soon as it's conjugated, so it's right between that, it's almost a full or it's quite a bit shorter, from 1.54 to 1.47. And if I put it between a pair of like a triple bond and a double bond, or two triple bonds, it's almost as short as a double bond, because an actual double bond is going to be about 1.33 angstroms. So it's getting significantly shorter. So that is telling us that something's going on. Well, what's actually happening is explainable by looking at the pi system. What I mean by the pi system, we know from looking at it before that the butadiene forms these two stable pi bonds, has these two little bit more unstable antibonds, but the two electrons from each double bond go to those two lower orbitals. And this lowest one's acting like one whole system that actually treats all the carbons kind of the same, and the next higher up one has a single node in it. Well, it turns out this does have that 2 and the 3 position kind of acting like a double bond. This one actually is acting more like a single bond. But the fact that this exists is why that bond got shorter. It is simply shorter because of the nature of a pi bond when it's all in phase with each other. All right. Next little diene that we have to actually talk about is our allenes. Now, allenes are double bond. So they're right next to each other. One carbon is double bonding twice. All right. This creates a weird stereocenter. What I mean by that, that's what we're drawing the mirror here for. Since that central carbon, the p orbitals have to be 90 degrees to each other, the pi bonds are actually 90 degrees to each other, and therefore these two end positions are 90 degrees from each other. And more importantly, this thing can't rotate. So the orientation of these things is fixed. It even has a situation where if these are 4 different things, there is a special set of naming rules that we have to use to actually name an allene. We're not going to be doing much of that. Just wanted to introduce you to the class right now. We will see more in allenes later. Okay, next thing we're going to talk about is that stability of our cations. Now, we already introduced this, and we actually pointed out that those allylic cations were quite stable. But we're going to see that there are also benzylic cations, where it's just the cation is right adjacent to a benzene ring. Now, these cations actually drastically change our reactions simply because they make very stable cations. Allylic cation resonates back and forth. Benzene actually resonates back and forth. The neat thing about benzene is it puts it into 3 different locations of that ring. Now, what is kind of odd, the benzylic cation isn't necessarily aromatic in some of these, or in these 3 resonance contributors, because each one of these, I got 1, 2 pairs of electrons, kind of half on this one because of those pair, but it's not necessarily aromatic. That's okay, because it's not staying that way. We're just moving out that charge all the way around. All right. Now, if I were to take our cations from before, so we had our methyl, primary, secondary, and tertiary, and all we're going to do is add our allylic and benzylic, we're going to see something like this. So, and we did add the vinyls on this little chart. So we did talk about this in our cations chapter, but we didn't have it on our table. It's on our table now. But our benzyl cation and our allylic cation are pretty much considered to be as stable as the tertiaries. Now, if I had a toss-up between a tertiary and an allylic tertiary, the tertiary allylic would be more stable than just a tertiary. Okay, now we're going to see that delocalized effect does actually affect our pKa's a lot. Anytime we see a compound that we know what its pK is should be based on the family it's in, like our ethanols, our alcohols always have pKa's around 15. But if I have that OH attached to a carbonyl, I do expect it to be much more acidic because now it's a carboxylic acid. Well, that change isn't because OH is behaving different. It's because that carbonyl helps provide us a resonance contributor. So it makes it more stable. And that's all we're seeing here. Those resonance contributors make things work out better. And we see our pKa's affected by that. Phenol, for instance, doesn't actually behave like a typical alcohol. Alcohols have pKa's in that 15, 16 range. Phenol has a pKa around 10. And the reason it's that much more acidic, think about ripping this off. If I rip that off and leave a negative behind, well, that negative just jumps into there and then moves into the ring. We get these resonance contributors to help stabilize it. And simply because that phenolate ion balances out those charges, we see phenol being a lot more acidic. All right. Aniline does the same thing. Well, aniline is actually our benzene ring with just an NH2. Protonated aniline, we've just added an H to it. We've taken away that lone pair. But that makes sense that we could take away that lone pair because this is actually going to stabilize that charge. That charge can move into the ring and move all the way around and stabilize itself. Can't do that with just a protonated amine because there's no distribution. There's no delocalized electrons to move towards that charge. Okay. Turns out our reactions of our alkenes will get varied somewhat by this delocalized effect. Now, benzylic one really affects it kind of only one way. We don't ever have to worry about too much on mixtures if you actually have an alkene right next to benzene, because even though Markovnikov says we add our H to the side with more H's, and in this case, neither side necessarily has more H's, we would expect 50-50. We don't see that. And it's because, well, we summarize Markovnikov to say the H goes to the side with more H's. What he actually said is we form the most stable carbocation. And benzylic is a very stable carbocation, and especially if I tried to compare it to the non-benzylic version of this. So leave that CH. Actually, I need to make that CH2 and leave this, the cation. This is just a secondary carbocation. This is benzylic. No comparison. So actually, I'm only going to go benzylic. I don't even see that thing form, so we're only going to get one product, never any mixtures. And that's the case always. If you can form a benzylic cation, even if it takes a hydride shift or a methyl shift, you're going to form a benzylic cation. So that's nice. You don't have to worry about any weird mixtures. If you can somehow create a benzylic cation by adding HBr to your structure, that's where your bromine's going to be, is in that benzylic position. Now, when it's isolated, it's with an isolated double bond, it's just going to behave like two separate alkenes. So on this, I see totally isolated. I just say the HBr, the H goes to the side with more H's, Br goes to the other. And if it's in excess, this side actually happens the same way. H goes to the side with more H's and Br goes to the other. It's just going to behave just like an alkene. The conjugated dienes are going to be a little bit different, though. And that's what we're going to spend a couple moments on here. All right, so here's what happens with our conjugated dienes. And I'm just doing a standard addition, chlorine for one and HBr on the other. But I want you to notice that I am getting something that kind of looks what you'd expect. So just adding right across one of the double bonds. So like it's isolated. Even the HBr, we go to the H side with more H's and the Br goes the other. So you are seeing what looks like a addition across the double bond, but you're also seeing this other product where the other thing attaches on the far end of the molecule. Well, that's the only thing that really happens. We call these 1,2 products and 1,4, and it's because we've numbered our diene 1, 2, 3, 4, and we're going to add a chlorine to the 1 position and a chlorine to the 2 position, or a chlorine to the 1 and the 4. And same with HBr. H goes to 1, Br goes to 2, H goes to 1, Br goes to 4. That's how our 2 products come about. So we are going to get mixtures on this. Now we're going to see if we can figure out how we can determine which one's our major product. All right, so we're always going to get a 1,2, 1,4 addition. I don't want you to think that we're getting a 1,2 dibromo or a 1,4 dibromo, because what we see here is I have a much longer chain. The 1,2 and 1,4 come from that butadiene part of the molecule. The conjugated system is 1, 2, 3, 4. And you add 1, 2 of the across the double bond, or 1 and 4. Okay, let's look at what's going on here so we can actually see what's going on, why we get the 2 different products. All right, first step looked very similar to what we've seen before on a double bond. Double bond attacks our H. H goes to the side that's got more H's. So we have it on the outside, making this the carbocation. But this particular carbocation is allylic, so it's going to resonate back and forth between these 2. And then the bromine attacks one of those 2 locations, and we end up with our 2 different products. Okay, let's see if we can figure out what's going to happen and why we get 2 different products and how we can control it. All right, turns out we always have what we call a kinetic product. It's the product that's formed fastest. Now, the fastest one is typically, or it's always, the 1,2 product. Now, the reason the kinetic product is always the 1,2 is kind of odd. For a long time, the 1,2 product was thought to come about because the transition state on that second state was more stable. Turns out that's totally wrong. Has nothing to do with the second step telling us which is going to be more stable. The kinetic product happens because of proximity. So what I mean by that, when that first thing happens, that H gets added onto, got deuterium here, but it's still going to behave like an H. When it goes on and creates that very first carbocation, at the moment it was attached, the halogen's right there. Even if we back up to our initial mechanism when we drew it, I'm going to just reposition this. If I were to say the H was hanging out here, well, it's never by itself. The bromine's right with it. So when this attacks, what we would say is the kinetic product happens because, yeah, this came up and formed that negative, but at the same time, this formed a positive. They're right near each other. The kinetic product forms simply because they're there. They're close. So the 1,2 product was always the kinetic product. Now, the thermodynamic product is the more stable product always. And all we mean by the more stable product has nothing to do with where the H and the Br is. The more stable product here is which is the more stable alkene. This alkene has 1, 2, 3 hydrogens off of the double bond. This one here only has 2, so therefore that is the thermodynamic product. And that works on all these. If I back up to our previous ones, we have 3 hydrogens off the double bond, or 2, so this is the thermal product. And 2 hydrogens, 2 hydrogens. Neither one's a thermal product. So this has no thermal product. But we can always make that call based on just which makes a more stable product. Now, the reason this was wrong was because the first step only creates one intermediate. Now, in this case, our intermediate, the H goes here, and we had those 2 stable allylic positions. Well, the intermediate's not one or the other. The intermediate is that weird hybrid that forms where that double bond is moving around. And this is partially positive, and this one is partially positive. We need to add some more H's there. Got to add this H. But both those exist simultaneously. And while, yes, this is true that when that bromine starts to attach, one might be more stable than the other, that is actually only going to help us explain what goes on this final product. And I really don't care how big this hill is. What gives my thermal product is how small the final product is, how low this is. I don't care anything at all about that peak. That's always going to be the slow step. I just care about how far it goes down. And the kinetic product, where this thinking failed, this thinking was happening based on that second step, what carbocation is formed. But the kinetic product happened right here. Once we actually formed it, once we made this carbocation, we were actually in a proximity. Bromine was just close enough to it. All right, let's practice on one of these. A little bit more complex. I have 1,3-pentadiene with a methyl in the 4 position. So I'm going to draw this with just my carbons. Pentadiene, 1, 3, and I will put a methyl here on the 4 position. 1, 2, 3, 4, 5, 4. All right, and we're going to react this with HBr. Okay, now what we haven't really pointed out, and I've done it on purpose, is that technically I always have 2 possible 1 positions on that 1, 2, and 1, 4. I could have the H get attacked by this carbon, or it could be attacked from this one. And what I mean by that, I have 2 potential sets of cations. All right, now, there is a reason this is the one that's going to attack. And it has a lot to do with the fact that, remember how Markovnikov, we want to say we want to put the H on the side with more H's? Well, this particular one has 2 hydrogens. This particular one has no hydrogens. So that's not a good 1 position. So my carbocation that I'm going to create at first is going to look something like that. And therefore it's going to resonate with this one. I'm just moving these back and forth. All right, and because these are my 2 products, or carbocations, I know I'm going to get one where the bromine's at this location. And I'm going to get one let me just wrote too big for a second. Where the bromine is there. Now I know this one's the kinetic product because it has the hydrogen and the bromine at the exact one double bond. My thermal product is going to be which double bond has fewer hydrogens. This particular one only has 1 hydrogen right there. This one actually would have 2. So in this case, my kinetic and my thermal product are the exact same thing. Now, knowing you have a kinetic and thermal product helps you out quite a bit on making one product stand out. Turns out, if they are different, you can actually drive the reaction to favor one or the other based on the temperature. A low temperature always favors the kinetic product. A high temperature always favors the thermo product. Now, rather than actually ever write temperatures, we always say high temp and low temp. Because higher you go, the more likely you are to favor the thermo product. The lower you go, the more favorable to the kinetic product. How high that is and how low that is will depend on your lab. I mean, here, I think it'd be very hard to get to negative 80 in a reasonable lab. I mean, dry ice, get us close. But that's really darn cold. Okay, I skipped That's the one we just did, where thermo and kinetic were the same. Looking at another one, and what we can do to speed up the process. We look at our 2, 1 positions. They both have the same H number. So we just choose to make one the 1. Therefore, our 2 locations we got there for a possible Cl or here for a possible Cl. And that's how we come up with our products. Now, if we put it at that second location, their double bond moves in. So we can actually make that prediction a lot quicker and what it is. Now, once we have our final products, we can decide the kinetic because that's always the 1, 2. And the thermal is based on which double bond has fewer hydrogens on it. This particular double bond has 2, that one has 2, so there is no thermal product on this one. Okay, next little reaction class we're looking at is something called a Diels-Alder reaction. Now, it always has the same 2 components on it. It's always what we call a 1,4 addition. What that means is we're going to take a conjugated diene that has a 1, 2, 3, 4 position, and we're going to add to it a dienophile. And that's going to end up making a ring with whatever this group is that was on the dienophile as a substituent. Just takes heat to do this. All right, what's actually going to happen is that conjugated diene actually always forms a shape such as this. Almost looks like a cis type form. And the dienophile just comes in here. And our transition state shows our dienophile moving into a state where this is slightly negative and this is slightly positive. And then this double bond attacks, and then we move that around. We get a nice little concerted reaction where the 3 pi bonds turn into 1 pi bond and 2 new sigma bonds. But it is what we call a concerted reaction. All that bond breaking and changing happens simultaneously. So the orientation of the dienophile and the diene is very specific. It almost needs to look like that 6-membered ring before it goes together. And because of that, turns out the conformation of the diene is darn important. Like this guy right here, because the rings hold it like it is, cannot actually do a Diels-Alder because it can't be orientated so the 2 double bonds look like they're cis. Now, the weird thing is these do have specific names. That single bond, even though most single bonds rotate, those 2 actually find those 2 different conformations far more likely because if it is planar, then this is a pi system with all 4 of those p orbitals together, and same thing here. So these 2 conformations are far more stable. So this bond, while it can rotate, it typically tries to stay mostly in that S trans because that gets our groups far enough away, but it does actually stay planar. It does look like it's a trans bond most of the time. But it can move. This doesn't take a lot of energy to rotate to the cis form. This one would because you'd have to break one of the rings apart. All right, something else that happens that actually drives this along. We need to have on our dienophile something that's withdrawing of electrons. Now, the reason that is that withdrawing of electrons will create one of those resonance contributors that has that end down there slightly positive. And that slightly positive is actually going to much more easily attack our dienophile or our diene, because what happens with our diene, think about our resonance that we know happens. This being a positive now and this being negative, and if I move that dienophile right down there below it with that positive and that negative are going to be attracted to one another. So the nature of those resonance contributors help drive this reaction or that mechanism. And having a withdrawing group on there helps make that even more positive. All right, that nice little contribution can actually can happen a lot of ways. Our dienophile can be some carbonyls. It can even be some more advanced carbonyls. But our diene and our dienophile can come with various different sources, and they all do these little Diels-Alder reactions. And all we can visualize is we're going to make a new bond here, and new bond here. New bond here, new bond here, new bond there, new bond there. We always make a nice little 6-member ring. If I were to number this 1, 2, 3, and 4, there is always going to be a new double bond between 2 and 3. And then a new pair of sigma bonds going from 1 and 4 towards that new molecule, where the other molecule was. All right. There is a weird thing that happens if I start with a dienophile and a diene that have groups on it. So we already saw the dienophile having a group on it, and we're going to draw that a little bit differently down here. And this diene also has a group on it. So we're drawing it down here. All right, all we're going to do is actually visualize flipping the diene upside down, but leaving the dienophile right side up. And you can see that these two could react to go to form this one. These two could react to go that way. And it seems like it shouldn't make a difference on how it's oriented. So you might even be safe to expect this is about a 50-50 ratio. Well, it turns out it's not. This is definitely the major. Now, the reason it's the major, we have to look at the resonance contributors here. All right, now we already kind of saw this one. This one actually has that pair move up here, this pair move up here, and that particular position gets to be slightly positive. We saw that. That one's what the electron withdrawing groups do. All right, but this one, that's more like an electron donating group because it's oxygen with lone pairs on it. So we're going to move this down here, which moves this, which moves these here. So our resonance contributor for having the OCH3, that's going to be slightly positive, double bond. And this is going to have a lone pair be slightly negative. And now our negative and positive would actually be attracted to each other. And that negative still exists here, but if you think about it, they're going to want to flip around to orientate themselves, right? And that's actually exactly what happens. Our donating group on the dienophile make one side more negative. In that case, it's this one. The dienophile, as a withdrawing group, makes one side more positive. And the negative gets attracted to the positive, forcing the orientation of a particular way. All right, we can do some more complex rings. All we're doing here is actually starting with something that already has a ring. Now, if it already has a ring, when it actually creates this new ring, it wouldn't actually break the first ring. So that first ring still exists. That's what's going on up here. And then we've created a new ring. So it's now two rings that are bridged together or combined. That's where this bridged bicyclic name comes from. Now, something else that's different on this. If you notice, we have that electron withdrawing group, the carbonyl there. You notice how it says 74% of the time it's down here as opposed to up? The biggest reason that happens, that endo position where it's up underneath, is found far more often, and it's mainly because this electron withdrawing group, remember how it's withdrawing? Well, it's going to be attracted to that lone pair. So it's going to be more stable in that initial transition state, being close to where the double bonds were or are going to be. So endo is always more stable. Therefore, we see it as a major product. All right. Also on stereochemistry, whenever we do the attachment, think about this. So this was, better way to draw this is not this one. Better way to draw this one is to have that CN up here. So when it attacks to our diene, it could orient itself going up or down, and this is an asymmetrical center. You will get both, and you're going to get a racemic mixture, always. So equal parts of each enantiomer. Now, if you start with a cis or a trans dienophile, You don't necessarily get distereomers per se based on that, or you don't get all the distereomers. What you will get is they will stay oriented the same. So if they were both on the same side of a cis molecule, they're going to be both on the same side of a ring. If it was opposite, they're on opposite sides of a ring. And you're going to get the enantiomer. And that's what this other thing is. It is the mirror of it. And that's what you get. You get one structure and its enantiomer. Now, one of the last things we're going to do is let's think about going backwards. Let's say you wanted to make that molecule and you want to do it with a Diels-Alder reaction. How could you predict it? Well, you know that the double bond must be the 2 and the 3 position of your diene. So that defines where 1, 2, 3, and 4 are. Therefore, these are the new bonds. We're going to split it apart. This had to be a diene, so we're just going to add a double bond back to it. So let's try to predict it on something more complex. Not that one. This guy. All right. We know the double bond must be 2 and 3. So this must be 1 and 4. And that is where our 2 molecules are split. So we do have our diene. And then the dienophile has that C triple bond N attached to it. I had to add that double bond back there. And one more complex. We have 2 possible double bonds that could be it, but this is kind of symmetrical. So there really is only one way of thinking about this. This is either 2 or 3, or that's 2 or 3. Therefore, this is 1 and that's 4. So you're creating new bonds to what would be a double bond. So I'm going to add a new pi bond here. And this must be the original structure. Instead of having a double bond at 2 and 3, it's at 1 and 4. And then my dienophile must have been a triple bond. All right. Plenty of practice on these things. I would encourage you to do every single problem in the back of your textbook to get more comfortable doing this, and even the problems in the text. And then look at the practice test and fire away on any questions you have.